first an important theorem called the extreme value theorem. Okay. I wonder what purple looks like. Oh, that's kind of nice. Okay, that's all right. We'll stick to blue. So we have the extreme value theorem. Okay, so if f is continuous on a closed interval, a, b, then f achieves both an absolute max and an absolute min on AB. Okay, so very, very important. The two hypotheses of this theorem that if f is continuous, so f has to be continuous, and it has to be a closed interval. If those two hypotheses are satisfied, then the conclusion is that f has an absolute max and an absolute min on that closed interval. It might be inside the interval. In other words, it might be a local max or local min where it achieves its highest, or it might actually be at the endpoints. Because it's a closed interval, the endpoints are part of the domain. So if it's continuous, if it's a closed interval, then both absolute max and absolute min are achieved. If one or both of the hypotheses are not satisfied, you cannot conclude that it has a max or a min. It may or it may not, but you can't conclude it. So if a function is not continuous on its domain, if the interval is not closed, all bets are off. So let's go ahead and take a look at a couple of examples of that. I'll do this in red. So we've got something like that. So let's go something like that. Okay, so here's A and here's B. This is a closed interval. The function is continuous. Therefore, it achieves its local max. It achieves its absolute max and absolute min somewhere on this interval based on the extreme value theorem. Well, in this particular case, here is your absolute min. I'm reversing everything today. This is your absolute max. Sorry. And this is your absolute min. Now, in this particular case, for this function, they also happen to be local maxes and local mins, but that doesn't matter. Continuous function, closed interval, it achieves an absolute max, it achieves an absolute min. Okay, let's look at another graph. Okay, this is A, this is B, continuous function, closed interval. We have the absolute min, we have the absolute max on that closed interval, always. And let me draw a little open circle, something like that. Okay, this is A, this is B. This is a closed interval. However, the function is not continuous. Therefore, it does not achieve both an absolute max and an absolute min. Here, I see some absolute max, but there is no absolute min, because in this particular case, this is an open circle. So it gets smaller and smaller and smaller and smaller, but we don't know how small it actually gets. So that's it. There is no absolute smallest value of y on this. There isn't, because it's discontinuous there. Doesn't satisfy the hypotheses, so it does not apply. Does not apply. And then we'll do one more. We'll take the function f of x equals 1 over x, your standard hyperbola. Well, here there is no max, there's no absolute max, and there is no absolute min. And the reason is, it's continuous, but there is no closed interval. I haven't specified a closed interval that has well-defined endpoints. So this is just going to keep climbing and climbing and climbing. This is going to keep dropping, dropping, and dropping. That's it. Now you might think to yourself, well, wait a minute, in this particular case, can't I just say that 0 is an absolute min? No. What 0 is a lower bound. In other words, the function will never drop below 0. But I can't say that there is a smallest number that's still bigger than 0 that this function will hit. It's going to keep getting smaller and smaller, heading towards 0. So in this case, like that one, this number is a lower bound on this function. In other words, it'll never be lower than that. But that doesn't mean that that is an absolute minimum, because it doesn't achieve its minimum. Because for every number I find that's small, that's close to this lower bound, like close to 0 over here, I can find another number smaller than that, closer to 0, smaller than that, closer to 0. That's the whole idea of this infinite process. So there's a very big difference. A lower bound or an upper bound is not the same as an absolute max, absolute min. Absolute max, absolute min, they have to belong to the domain. So the x values at which the absolute max and absolute min are achieved, they have to be part of the domain. That's it. Okay. Excuse me. So let's move on. Now, one more theorem here. Let's go ahead and leave it in red. Okay, if f of x, excuse me, if f of x has a local max or a local min, at C in the domain of the function, then f prime at C is equal to 0. All that means is the following. So we already know what local maxes and local mins look like. Local min is a valley, a local max is a crest. So if I have some function like this, well, this is a local max, and this is a local min. So we'll call this C1, and we'll call this C2, whatever the x value happens to be. This says that at the local max and at the local min, the slope is 0. The derivative, f prime at C, is 0. The derivative is 0. The slope is 0. And we can see it geometrically. We're going to have a positive slope from your perspective as you're moving from negative to positive. Positive slope, it's going to hit 0, and then it's going to go down like this. That tells us that we have a crest, a local max. And then this one, local min. That's it. That's all this theorem says. Okay, so now let's go ahead and give a definition. Excuse me. Definition, something called a critical number or a critical value. Critical number or a critical value. Okay. A number C that is in the domain such that f prime at C equals 0, or f prime at C does not exist, that's it. A critical number or a critical value of the function, it is a number in the domain such that it's a number C in the domain such that f prime at that number is either equal to 0 or f prime at C does not exist. So in this particular case, these values, well, f prime at these values is definitely 0. It's a horizontal slope, so these are critical values. That's it. An example of one where it doesn't exist is the absolute value function. Absolute value function goes that way, and it goes that way. Well, here, it's continuous there at 0. but it's not differentiable there. So because it's not differentiable there, that's a critical value of the absolute value function. That's it. So f prime at c equals 0, or f prime at c does not exist. Now, if it's not defined there, that's not considered a critical value, okay? So it has to actually be defined there. It has to be in the domain. That's important. If it's not part of the domain, then all bets are off. Okay, so the procedure. Let's actually write this a little bit better. And let's do it in red. So the procedure for finding the critical values, very, very simple. The procedure for finding the critical values of a function f of x. Very, very simple. Find the derivative. Find the derivative f prime of x. And 2, well, equals 0. Set f prime of x equal to 0 and solve for all values of x that satisfy this equation. For all values of x that satisfy this equation. That's it. This equation. The only other thing that you have to watch out for is, again, places on the domain